Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss some concept illustration problems on radiation pressure. So in this case, you can see that there is a uniform radiation of intensity I which is exposed on a cone of height h and radius r. The surface of the cone is perfectly absorbing. So we have to find out the force acting on this cone. So in the case of the cone, when surface is perfectly absorbing, we can just multiply the radiation pressure and the cross-sectional two-dimensional area of the cone to find out the force. So we can write down the force as the radiation pressure, which is I by C, into the cross-sectional area, two-dimensional area of this cone will be the area of the triangle, and the height of the triangle is h, and this is 2r. So the area of this triangle will be half 2rh. So the area will be rh. So the answer will be IRH by C. So this will be the force acting on this cone. So the correct answer is D. Now let's move on the next question. In this problem, you can see that there is a spherical concave mirror that has aperture diameter D, and the radius of curvature of the mirror is R. So there is a point source of light that is placed at a center of curvature of this mirror, and this source emits the light of power W. The mirror surface is completely reflecting, and we have to find out the force acting on the mirror due to this light. Now obviously the situation is this, that this source is kept at the center of the mirror, center of curvature of the mirror, and let us suppose that this is mirror. So light will be going normally through this mirror and it would be reflected back on the source like that. So we can say that the force acting on the mirror surface will be, obviously the pressure will be 2I by C due to the fact that mirror is completely reflecting, and multiplied by the two-dimensional cross-sectional area. So the two-dimensional cross-sectional area directly is pi d square by 4. Okay, so force will be 2 by C, and I is the intensity at these points. So intensity at these points will be the power upon 4 pi r square. So I will be W upon 4 pi r square into pi d square by 4. So this F would be equal to W d square by 8 r square C. This will be the force acting on this mirror. Now we move on the next question. In this question, you can see that there is a point source of light having a power of 500 watts. It is kept at the focus of this convex lens of aperture diameter D. The focal length of the lens is 2D by 3, and assuming that the power which is transmitted through this lens is only 40% of the incident power on the lens, and the surface of the mirror is perfectly reflecting, so we have to find out the force acting on the mirror. First of all, we know that the wavefront which is incident on the lens will be spherical, as well as the wavefront which is transmitted through the lens will be plane wavefront like that. Okay, so first of all, let us see that what is power transmitted. So let us suppose that power incidence is Pi and power transmitted is Pt. So power incidence is, obviously you can say that this source is emitting a spherical wavefront, and total power 500 watt, this is P naught, is distributed in this complete sphere. So if we find out the power in this area only, so we have to use the solid angle analogy. Okay, so therefore to find out the solid angle, first of all let us draw this cone. This is the cone. If this angle is theta, so you can see that this distance is, let's suppose, r, and r will be equal to under root of 4d square by 9 plus d square by 4. So r will be equal to 5d by 6. This is r. And cos theta is equal to 2d by 3 upon 5d by 6. Okay, so cos theta will be 4 by 5, and the solid angle will be equal to 2 pi into 1 minus 4 by 5. So this will be equal to 2 pi by 5. This is the solid angle. And we know that P naught, which is 500, let's suppose it is P naught. So power incident will be equal to P naught by 4 pi into 2 pi by 5, because total power P naught is distributed over the solid angle 4 pi, and through this solid angle only this much power will be incident. So P naught divided by, it would be 10, so it would be 50 watts, because P naught is 500. Now P transmitted is only 40%, so P transmitted will be 0.4 of 50, so it would be equal to 20 watts, and the transmitted power will be in form of a plane wavefront, and therefore we know that force acting on the reflecting surface will be 2p by c, because the force is 2I by c into area, and I into area is power, so 2 times of power transmitted by c, so it would be 40 by c, where c is speed of light. So this is the force acting on this mirror. Now let's move on the next question. In this question you can see that there is an equilateral prism which is kept on a table, on a weighing machine in fact, which is kept on a table, and the refractive index of the prism is root 2. Now this prism is illuminated with a narrow laser beam having power P naught, and the wavelength of the beam is lambda. Now this laser beam passes through the prism in such a way such that it passes parallel to the base of the prism from the region inside the prism. So we have to find out the change in the weight of the prism due to this incident laser beam. First of all, we know that this is the case in which the deviation occurred in the beam is minimum, because it is passing through the base of the prism, parallel to the base of the prism. Therefore this angle will be 60 degree, this angle will be 60 degree, this angle will be 30 degree, and if this is I, so this will be I, because I will be equal to E for the minimum deviation, and del will be equal to 2I minus A. A is obviously 60 degree, and I can be calculated by using Snell's law, that 1 sin I is equal to root 2 sin R. R is 30 degree, so I will be equal to 45 degree. So this angle is 45, and deviation del can be written as 2 into 45 minus 60, so it is 30 degree. Now the momentum of this beam, incident beam, is like that, and the momentum of the reflected beam is like that. In fact, refracted beam is like that. So if we draw these two beams, so the change in momentum, see, momentum will be same because no amount of photons are absorbed in the material of the prism, therefore change in momentum will be in the downward direction. As well as you can see that if the x component of these two momentums is compared, then there is no change in the momentum in x, therefore the momentum change will be in the downward direction. Okay, and in fact it will be initially it was in this direction, and finally it was in this direction. So the change in momentum will be in the downward direction. Now we see that the momentum carried by the beam per second dp by dt is f, let's suppose, and it is f, and this f is equal to power p naught by c. We know this formula that f is power p naught by c. So delta p can be written as 2p sine this angle is deviation del by 2. So it is twice, if we talk about momentum change per second, so delta p by t, which is the change in the weight of the prism, delta w, will be twice of p naught by c, and sine del is 30 degree, so sine 15 degree. So this is the change in the weight of the prism. Okay, and obviously you can see that this force will be acting in the upward direction, because the force acting on the photons is in downward direction, and the force acting on the prism will be in the upward direction. So the change in the weight of the prism will be negative. It would become lighter. Thank you.